Ladies and gentlemen, welcome to the ISTS Institute for Security, Technology, and Society seminar and distinguished colloquium talk today. We're very fortunate to have as our speaker Professor Jaideep Vaidya from Rutgers University. Professor Vaidya did his undergraduate work in Mumbai, India, finished his master's and PhD at Purdue University, which is a top computer science department. And he's one of the leaders in the area of ensuring security and privacy for enterprise systems. He's published a ton of outstanding papers in this space and received numerous best paper awards from many different conferences in data mining, databases, security, and informatics. He's a distinguished scientist of the Association for Computing Machinery, and he's the editor-in-chief of the IEEE Transactions on Dependable and Secure Computing, which is basically the top journal in the field. Today, we're fortunate to have him speak to us about how to identify anomalies accurately and privately, something that has, as I was discussing with him before the talk, an enormous number of applications. So without further ado, let me hand the I would say microphone, but the Zoom controls over to Jaideep. Before I do that, let me remind everybody, you will probably be on mute right now if you're one of the audience. But if you would like to interject, please raise your hand or insert a question in the Q&A, and we will try to have those questions posed to the speaker. Again, you can raise your hand and one of the moderators will unmute you and give you an opportunity to ask a question. So with that, over to you, Jaideep.
Thank you, VS, for that very kind introduction. And I'm really happy to be here. I would have been happier to actually have been there at Dartmouth, but no matter what, it's a pleasure to present some of my work in this area. Before I go ahead, just a couple of things. Please do feel free to ask questions, or clarifications anytime that you feel, things pop up in your mind. It would be a lot nicer for this to be a conversation as opposed to, a lecture of any sort in any case. So today I'm going to talk to you about how to identify anomalies both accurately and privately. This is joint work with my PhD student Hafiz Asif and my colleague Pericles Papakonstantinou, a couple of others, but primarily this is work that I've done with the two of them, and we'll go through with this. So ordinarily, I was going to start off with the applications of anomaly or outlier detection, but the elephant in the room today is COVID. So I'm going to talk a little bit about this. All of us know what's been happening with COVID, so I'm not going to spend time here, but we do know how the number of cases has kept on increasing, rapidly, so to speak, in fact, exponentially at certain times. And there's a huge problem in the world, and more specifically in the US as well, where the number of cumulative cases have just kept on going up. And now we seem to be having a second wave coming in as well. Now, you may ask, what does COVID have to do with anomaly detection or outlier detection? And the point here is that if you want to figure out what are the hotspots in the country, if you want to figure out which areas need to be locked down, if you want to be smart about this, that is actually an anomaly detection problem. That is precisely trying to figure out, especially not just over space, but over time, what's the behavior and which are the spots that look different, that look anomalous. So this is an anomaly detection problem, and I'll come back to it in just a minute. But before that, I want to talk about this a little bit more. When we look at what has happened, what has unfolded over the past, I would say 9 or 10 months now, the key problem, and we've seen this, in fact, all over the media, you look at the New York Times, it basically says, hey, testing, delays in testing set back the coronavirus response. You look at Washington Post, same thing. They basically say it was testing. Okay, there were delays in the testing. There was under-testing that was going on. Same thing with USA Today. And lest you feel that this is just the liberal media, so to speak, that are talking about this, that's not true. If you look at conservative outlets like Forbes, or if you look at Wall Street Journal, they also say precisely the same thing, that it's really more COVID-19 testing that would be the answer, or that's what has been causing the problem. To a large extent. So months into the pandemic, we still don't have any easy answers on coronavirus testing. So we've seen this problem that has occurred, and it clearly is a health problem. But I put up the Wall Street Journal as well, just to point out that even from an economic perspective, the issue really is that we need to be able to test, and that is what will basically enable us to open up parts of our economy and so on. So I like this graph that the New York Times put up, is your state doing enough coronavirus testing? And broadly, the answer is no. Okay, it's definitely not. And again, the Wall Street Journal saying, hey, you know what, COVID testing, not a cure, is what investors need to watch if they really care about what's going to sort of happen. All right, so we see the problem has been testing, the under-testing and under-resourcing of this. Now, from our perspective as technologists, technology in a way has tried to come to the rescue of this. And many of you, or most of you, are probably aware of the apps that have been put up in terms of crowd sensing, in terms of finding out, what is the situation out there right now. So for example, there's the COVIDNearby app, where you can put in symptoms and then you can see overall, what's the situation. There's the How We Feel app, so to speak. There's also the CMU app, which is in partnership with Facebook, where again, you put in the survey. Mostly you're just putting in your symptoms, if you will, and then you effectively get to see this sort of a figure, a heat map or whatever, which will give you some idea of what the situation is in a local sense. So that's fantastic. And in fact, this was done to some extent with the flu as well. So crowd sensing was used as an alternative, and similar efforts right now have been done for COVID as well. So that's great. But, and here is where I come into the picture, a critical problem is privacy, okay? And again, there have been lots of different cases in the past. I'm going to come back specifically to this COVID case, but, almost a decade ago, you had issues with AOL where we were able to re-identify people. Netflix released the anonymous data set. It was not anonymous any longer. Same thing has happened with genomes, genomic data, where it turns out it's really not anonymous the way you think. So even though these apps, and I don't know how many of you have actually clicked on the link to the privacy policy, if you will, of those apps or looked at what's happened. I've gone through all of them, and almost all of them, they basically say, okay, we are aggregating data, or we're stripping the identifier, and that's all that they are doing. Okay, what I'm saying is that is actually not enough. And I have one example in the healthcare space. This is some work that we actually did just to show you, clearly what would be the problem if you just did aggregation or stripping of information. So there's this project called the Healthcare Cost and Utilization Project. This is a really large project that is funded by AHRQ, the Agency for Healthcare Research and Quality. They actually take in data from all of the hospitals and inpatient centers across all of the US. So this is huge, okay? This is a phenomenally large project. They take in all of this data continuously, if you will, and what they do is that they create what are these so-called contingency tables, aggregates, if you will, okay? And for people who are interested in just statistics, if you will, you can go make use of this HCUP.net sort of system, online querying system, and you can ask questions of the following form. So this is something that we asked. What are the number of hospital discharges in New Jersey of patients with ovary cancer in the year 2009? And we said we wanted it categorized by the age and by the race. And we got back this table where you get the numbers. The red stars are things that have been suppressed because they're coming from less than 10 patients or less than 2 institutions. Okay, and that's their policy if you think about it. So what we thought about was, hey, you know what? Okay, there is this system that HCUP.net is there. It'll let me retrieve information on specific diagnosis, conditions, procedures. I can pick different outcomes and measures. If I want to see how far people have stayed in the hospital, how many times they were discharged, I can characterize the patients and the hospital characteristics, their age, gender, and so on. Now I can try to fill in some of this information. So we wanted to see to what extent is this possible. Can I create these linear programming models, run branch and bound algorithms to sort of infer the bounds. So one thing, I just wanted to show you this particular example for a minute more, if you will. And if you look at this, I'm assuming you can see my mouse as well. The red stars, right? So this one is kind of meaningless. You're giving me everything in the row except for this. So clearly I can fill, I know that's one person. And the same happens in these two cases as well. The other cases, you might feel a bit more protected, but the answer is you're not. We can view those as variables. And now, because I know all of the rows sum up to the values and all of the columns, I can do this max and min. I can create these problems, optimization problems, and get very tight bounds very, very quickly. So in fact, for this particular thing, I learned that the single Native American is precisely in the age group 65 to 84. And remember, I already know the gender because it's ovary cancer. It's a female that we are talking about. Right, and I'm getting fairly tight bounds on some of the other things as well. Now, we actually did this. I don't want to go into more details on this, but if you combine it with all of the different queries you can ask, we could, for example, figure out that exactly one Native American woman with, woman with ovarian cancer went to a privately owned, not-for-profit teaching hospital in New Jersey with more than 435 beds in 2009. She didn't pay by private insurance. She had a routine discharge. She stayed in the hospital for a little over 33 days. The 33.5 is due to averaging, but I can show you. It's basically 34 days. Think of it that way. With her home residence being in a county with 1 million plus residents, and her age was exactly 75 years. This is horrible, right? So if you stop and think about it, if you remember Latanya Sweeney's pioneering work, you can re-identify 97% of all Americans if you know their birth date, the zip code, and the gender. And we have that and more over here, so to speak. So this was shocking, in fact, when we looked at this. So this work, by the way, we published this at the American Medical Informatics Association, their Clinical Research Informatics Conference. It, in fact, got the Distinguished Paper Award for this because they were as surprised because there was no linkage that was being carried out. So that's okay. The interesting part was that we told AHRQ about this. Okay, we informed them. We told them you have this problem. We gave them some technical solutions as well. And differential privacy was one of those. There were others as well. Any guesses on what happened? What did they do, so to speak? So did they implement anything or what have you? So we have people with a lot of experience here.
I'm guessing that you got a cease and desist order.
No, it was a little better. What they did was they changed it, and now if you go to HCUP.net and you try to do things, there's a pop-up that comes up that says, please don't try to re-identify people. That's it. That's their way of asking you not to do this. So that was a little demoralizing, but at least, all right, they did something, so to speak. So coming back to COVID, I talked about COVID and then I took this digression, if you will. But in fact, we looked at COVID-19 with respect to the apps. If you look at people, what is the potential identifiability of people? And it really depends on what region you're looking at. Okay, so if you're looking, for example, at a rectangle of, say, 0.5 kilometer, it turns out that between 0.8% to 40% of people can potentially be re-identified. They're unique in that particular box, if you will. And of course, if the rectangle size increases, it's like a kilometer long, then 1 square kilometer, I should say. So then it's 0.3 to 30%. And of course, again, the reason for the ranges, as you can imagine, is due to the density, right? So it depends on whether you're looking at New York or if you're looking at Hanover, New Hampshire, or here in New Jersey, what have you. And that varies. But this is bad. So this essentially tells you that, okay, you can aggregate and all that, but guess what? I'm going to be able to go back and re-identify a large number of such people. Okay, in this sense. So this was basically the reason we launched the research effort. Actually, it was funded by the National Science Foundation with a rapid grant, looking at how do we do crowd sensing in a privacy preserving way, and then how can we apply it, from the anomaly detection perspective to do sort of hotspot detection, to do ranking and so on. And this was funded both by the National Science Foundation, as I said, with a rapid grant, And I also got an outstanding research, investigator award from NIH. So that is also funding part of this. But again, this is joint work, with Pericles Papakonstantinou, my colleague, and Vivek Singh at the School of Communication and Information, Stephanie Shaw, who's basically an epidemiologist at Rutgers, Hafiz, who's my PhD student, and Julian Jarrett, who's at Lutron, but who's helping us with the software part of this. So with that, I have sort of built up a case for why we need privacy in sort of anomaly detection. But now I'm going to step away from this for a minute, and I'm not going to tell you how we've sort of done this. I'll wait on this a little bit. I'm going to talk about anomaly detection in general, and then come back to the specific case of COVID-19, the crowd sensing case that I'm talking about over here. And then I'll talk about how we've actually realized that in practice and some of the challenges there as well. So again, for those of you who are not aware of what outlier detection or anomaly detection is, it's basically trying to find anything that looks abnormal, that sticks out, if you will. And this is something that has broad application. So it's something that has applications in finance. If you're doing sort of credit card fraud detection, you're looking for insider trading, that's basically outlier detection. In healthcare, if you're trying to find malignant tumors or gene mutation, what have you, and even in the case of our epidemic or pandemic here, that's anomaly detection. In security, pure security itself, if you're looking at DDoS attacks, if you're doing intrusion detection, that's anomaly detection as well. And then in law enforcement, again, surveillance or terrorism, where you're trying to find these problem points, that's anomaly detection as well. And these are just a few applications. There are actually a whole host of applications. This is, in fact, one of the most commonly used techniques or areas in sort of data analytics as a whole. So this is a pretty important problem as a whole. Now, I'm going to look at one specific application of it because it's very easy to explain in this context, and then I can show you the privacy aspects of this as well. So let's just think about flagging, for example, money laundering transactions in a privacy-preserving manner, and I'll come back to what I mean by this. But for now, I'm going to use a very, very simple model. Okay. The identification feature is only the amount that is being transferred and the number of times such transfers have occurred. Okay, so whatever amount you've transferred, how many other transfers have occurred with that amount as well. So now an anomaly or money laundering transaction is something that markedly deviates from other records. Okay, so we are assuming that this doesn't happen all that frequently. It's something that is uncommon. What is normal, actions, maybe sending money to your family. Okay, immigrants do this all the time. Students, you would support your family as well. For college students, that's something that shouldn't be surprising, and so on. Okay, so this cluster of things would be what would be considered normal. This thing here is basically the anomaly or outlier. Clearly, accuracy is mission critical to this application. I don't want to misclassify these people here as anomalies, nor do I want to find, things which aren't there, so to speak, right? So both false positives is a huge problem. False negatives is also a huge problem in this particular space. Now, one point that I want to make in everything else that I'm going to talk about today, I'm going to focus on a data-dependent definition of anomalies, okay? So the difference, you can have many ways of doing anomaly detection. In fact, you could just use statistics. You could create rules that say, okay, if it is about this, it's an anomaly or what have you. But a very interesting case, which is used all the time, is this notion of data dependence. So for example, this thing is an anomaly because it sticks out. If, in fact, all the records had been of this type, it would be normal because it's no different from what everyone else is doing. Okay, so our primary focus is going to be on data-dependent anomalies. This, however, creates a huge problem because now there is a privacy puzzle, if you will. Okay, so if we have high accuracy, if I find this, obviously there's no privacy for outliers. That's obvious. I'm telling you who the anomalies are. They don't have any privacy in this sense. But the interesting part is that if now I say no privacy for outliers, then by definition, there is no privacy for data-defined normals because the notion of anomaly is data-dependent. So when I say no privacy for outliers, I can't just say, okay, I don't care about those people. I'll throw them under the bus, because you're throwing yourself under the bus as well. Okay, so since it is data dependent, so that's the critical sort of question over here. So what do we do? How do we resolve this conundrum, if you will? And the answer, I'm going to get to it in a little bit of time, but in brief, it is that somehow we have to ensure that we don't leak information about the so-called normals. Okay, that is who we are trying to protect. Let's focus not on who we are not protecting. We need to focus on what we are protecting and give very good guarantees over there. All right. So now for the rest of this part, I'm going to focus on how do we achieve this. Okay, and I'm going to start off with differential privacy. Why differential privacy? Because it's basically the state-of-the-art model that is basically used now, by the census, by Apple, by Google, what have you. But interestingly enough, I'm going to show you why differential privacy doesn't work in this particular application. In fact, not just doesn't work, it's impossible for it to directly work in this application setting. Then I'm going to give you a new notion of privacy. Okay, so I'm going to have a slightly different, very much inspired by differential privacy, in fact, based on differential privacy, but a slightly different notion of privacy. After that, so I'm going to focus on the definition and give you the key understanding of that. Then I'll talk about our two constructions. We have two specific constructions. One is a DP to SP compiler. The other is a individualized construction for designing mechanisms. I won't spend too much time on this. Again, if you're interested, please do look at the paper or feel free to ask me in any case. But I want to give you the intuition behind why things work as opposed to just going through the math necessarily. And I'll talk about how they are effective with the empirical evaluation as well. Okay. And then after all this is done, I'll come back to our COVID case and then talk about how to make it work in that setting. So before we go there, just briefly, what the setting is, it's very simple. We are assuming that there is a curator who has the data and is able to run algorithms on it. And then there is a querier who poses a question, tell me what are the outliers, or tell me whether this thing is an outlier or what have you. The curator runs the whatever algorithm it is, mechanism it is on the data and gives the answer. Okay, so we are assuming that the curator is trusted in this case. Okay, there are ways to get rid of this assumption as well, but that's a whole different field, secure multi-party computation, that I'm not going to enter for today. So we can forget about that and just think of the querier interacting with this so-called mechanism that, posing a question and getting an answer, whatever it may be. Now the database, again, for the rest of this talk, remember I said it will be a very simple setting, though this is applicable broadly, in fact, to multiple features and everything else, is that I'm going to look at transactions and the frequency, the value. So again, you can think of money. This is a very little bit, a little bit more. This is a lot of money. And then the bars, the histogram that you see here is the number of times this transfer is made with that particular value. So you can view the entire data set. This is not obviously the optimal way of storing this, but for now, let's just think of this, conceptually as a data set is basically a histogram. It's all of these raised to, whatever. So whatever the number can. Okay, so natural numbers raised to X, the types. All right, so now let me come to differential privacy. Again, I'll briefly go into differential privacy. If you already know of it, that's fantastic. If you don't, I'll give you a brief idea of how differential privacy works. So first of all, there was this question of, can we protect privacy, period? Can I give a complete guarantee over privacy no matter what is done? And it turns out that the answer is no. Okay, if somebody has a lot of background information about you, for example, if someone knows where VS lives and is able to keep track, then even if there are certain things that are done to protect, at the end of the day, due to that background information, you would be able to breach the privacy. Okay, so I cannot give you I cannot give you a complete overall guarantee that says, okay, no matter what, nothing will happen. What we can do is what is called differential privacy. And what differential privacy does is the following. Conceptually, think of two databases. One that has John's information. John could be anyone. I'm just looking at John right now. It could be VS, it could be me, whatever. Okay. And then the other database is identical to the first one. The only difference is that it does not have John's information in it. Okay. So these two are neighbors. This has John's information there. This is exactly the same as that, except it does not have John's information in it. And what we are going to say is that if a mechanism M, which operates on these databases, is private, okay, then what does that mean? It means that if that mechanism is run on this database, or if it is run on this database, the output that you get, the likelihood of getting that output is very much the same. And in fact, it turns out this has to be a randomized algorithm. It's a probabilistic output. No deterministic algorithm can satisfy, no non-trivial deterministic algorithm can satisfy differential privacy. So, but what we are going to say is that, okay, the mechanism is private if the likelihood of getting, any output from this is similar to the output you get from here. And the reason why, intuitively, why this protects privacy is very simple. Let's say my querier is posing a question and the querier gets an answer. Now looking at the answer, the querier can't figure out, was it coming from here or from here? So it means that the querier can't know whether or not John was in the database or not. Okay, it doesn't mean John's privacy will be guaranteed, because maybe, again, I have a lot of background information that would be problematic. What it does guarantee is that John has no added risk by being part of the database. Okay, and that's how, because this works for all pairs of databases and all outputs, it's basically a guarantee over everything. Okay, and again, this is just the probability of output. We'll forget about this. This is the formal mathematical definition. So, mechanism M with domain D is epsilon differentially private if for every two databases X and Y differing by one record, and every R, okay, so every possible output, the probability that you get this output, mx in the set of these outputs and my in the set of these outputs is bounded within e raised to epsilon. And it works both ways. So it's a tight bound both ways. And so this is great. Okay, differential privacy, again, Cynthia Dwork came up with this in 2006. And since that point of time, it has been used by a boatload of places, both government agencies and organizations. So again, Apple and Google are doing this right now. So is the census. In the 2020 census, we are using differential privacy to sort of guarantee things. So then, and that guarantees privacy. So fantastic. And then the immediate question is, okay, so can we use differential privacy if we are trying to do anomaly detection? Now, before we go there, I want to show you a very specific kind of anomalies, because that will help to sort of explain why things don't work. For that, I'm going to focus on the so-called beta R anomalies. If you've come from the databases field, you may have seen this as the PDT anomalies, distance-based anomalies that Knorr and Nugg defined back in the 90s, if you will. Okay, a very simple idea. Basically, you decide a record is an outlier or anomaly or not by just looking at its neighborhood and looking at the number of records in the neighborhood. If it's, I look and I see that within this radius, there are less than beta other records, then it's an anomaly. Otherwise, it's not. Okay, so the reason why this distance-based outlier definition is nice is because we basically assume that outliers make up a small percentage, which is true. I mean, it's only an anomaly if it happens rarely. Then there's a stability factor. A small change in the database doesn't necessarily alter the record's outlying behavior. And then the third part, the databases are sparse. I'm going to come to in a minute. That this doesn't depend on it, but that's something that will play a role in just a minute. Okay. Now, by the way, what I'm going to talk about is not dependent solely on this. You could use density-based outlying definitions like local outlier factor or whatever, that would work perfectly fine as well. But this is easy to understand, so I want to explain with this. And there's one more thing I'm going to talk about. Normally, the original Knorr and Nugg paper, they talk about outlier detection, which means given a data set, tell me what are the outlier records. Okay, so give me a list of outlier records. In fact, that is a pretty difficult problem when you view it from the privacy perspective. I'm going to look at a simpler problem. I'm going to say, let me pick a record, anything, and ask, is this an anomaly? Is this an outlier? So this question, does AX, is it an anomaly or not? Meaning on this algorithm on the data set, it just needs to answer whether a particular record is an anomaly or not. And that is what we call the anomaly detection function. And I'm going to show you that even for something this simple, differential privacy cannot give you a good answer. So let's go jump right there and talk about why differential privacy has poor accuracy. So it can guarantee privacy. That's not a problem. But what I'm going to say is that it cannot guarantee accuracy. Not guarantee, it's guaranteed to give you bad accuracy. Let's put it this way. So this is a simple example. Beta is 5, R is 1. we are looking at these two neighboring databases. They are exactly the same, except for this thing over here where there is one record, okay, on the in one. And in this we don't, in this we do have it. And again, any two adjacent records on horizontal axis have a distance 1. So over here, if I look basically and I ask what are the outliers, this is the only record which is an anomaly or outlier here. Here, both of these are outliers, okay? Now, clearly over here, this thing is not an anomaly because it doesn't even exist. It's not there in the database, so it's not an anomaly. Okay, great. Now, remember the question I'm going to ask is, in fact, this thing, this single thing over here, I'm going to do an anomaly identification of that. I'm going to say, is this an anomaly? Okay, and that's the question that I'm asking. So the true answer over here is no. The true answer over here is yes. Okay, so remember these two are neighbors and they have exactly opposite answers. Here the answer is no, here the answer is yes, which basically means that because of the differential privacy guarantee, the probability that whatever answer is provided, it doesn't match either this or this, the maximum of those has to be over 1 upon 1 plus e raised to epsilon, which is, by the way, very close to 0.5 for any reasonable value of epsilon. So that essentially means, boom, in a case like this, I am going to make a mistake no matter what on one case or the other. I cannot win both ways. I'm either going to get budged on the false positives or false negatives. And this brings the other factor that I wanted to talk about, sparsity. Okay, if you think about databases, especially when you think of all the features, databases are huge, but they are still very sparse. Okay, there are lots of empty areas. And the problem are indeed those empty areas, because every empty area, if you introduced one more point over there, that record, it suddenly becomes an anomaly, whereas it's not an anomaly when it was empty. So that means that for all of these empty areas, differential privacy is guaranteed to perform badly. Okay, and there are going to be a huge number of these questions where you're going to do very, very sort of poorly. And this is actually one of the data sets from Stony Brook that we looked at from the odds repository. And these are the outliers. These are basically the normal points. So you'll end up making mistakes, not just over on these points, but all of the white spaces as well. So that's, yeah, this is the outlier identification function. So we didn't want to stop actually right there. We wanted to think about, what is the reason? Okay, what is there a particular reason that makes this problematic? So remember this bound, so to speak, that, we'll make an error, the mechanism will make an error either on X or on Y. It has to be greater than this. When does that happen? It turns out that it's not just the data dependence that is the problem, it's really the existence dependent or existence dependence or independence. That's the key factor behind this, okay? So when you have existence independent outlier queries, you can use differential privacy, no problem, okay? But when you have existence dependent outlier queries, this bound will apply and you cannot use differential privacy. It's never going to work. So again, I know I went through this, so I'll just talk briefly about this. It's very simple. Existence independent outlier query is where the answer is not contingent on the absence or presence of any particular record. And examples of that are, is there a flu epidemic, or how many anomalies are in the data? It doesn't depend specifically on the one particular record. But questions like what are the outlier records in the data, or is the record I an outlier in the data? It definitely is contingent on the absence or presence of a single record. And that means you cannot use differential privacy in this space. Okay, our bound applies and it's impossible for you to go ahead and do this. So a principled approach to private outlier analysis basically says, okay, let me look at the outlier query and figure out, is it existence dependent or not? If it's not existence dependent, it's independent, then great, I'll just go ahead and use DP. But if it is existence dependent, I'll try to reduce it to a set of queries of this kind, and again, try to use DP. But in the worst case, I'm going to end up over here. And there, I will have to use a form of relaxed DP. All of the generalization and variants, in fact, don't work, and you need a new notion over there. So now I just want to tell you this new notion that we are proposing called sensitive privacy. which is very nice. In fact, I'm very happy with this work because it actually guarantees utility as well, while providing the best possible privacy guarantee that can be done. So for that, I just want to show you, I want to juxtapose what we have versus what we want, okay? And then I'll show you that it's achievable, okay? So what we have in differential privacy is basically this case where we have the same privacy for everybody. It's guaranteed for everybody across the board, okay? So you get this case, and this is a mapping of privacy, and you see all of the points. This is synthetic data, but it's just to show what's happening. You have the same level of privacy for everybody. What it ends up resulting in is, of course, differing accuracy. You still do pretty well in the super dense area, no problem. But everywhere else, this error is very close to 0.5, which is the same as causing a toy. So you're going to suffer everywhere else. What we do want, and in fact, the great part is that we are able to achieve this with sensitive privacy, is to vary privacy by outlierness, okay? So we want to guarantee privacy for everything that is normal, okay, or even potentially normal. It's only the anomalies where I'm going to now trade off and not essentially give you privacy, okay, as much privacy. In fact, it varies. It's not a fixed yes, no, it's how much, if you will. And the result of this is that the accuracy is really nice because you get accuracy not just for the green part, but for everything else as well. In fact, the anomalies as well. The problem is only at the boundary. Okay, the boundary we also suffer from, but the hope is that there are very few things that are actually on the boundary, so to speak. And I should point out that this over here, by the way, is the optimal DP mechanism. So it's not just something I came up with or that you could come up with. It's the optimal DP mechanism. It's guaranteed to have this bad result. And this is the result of our SP mechanism, what we've been able to sort of achieve. So let me give you the intuition behind sensitive privacy, the definition itself. The idea is that we are going to protect the privacy of every record that either is normal or becomes normal under a small change in the database. Okay, so if you are normal now, or maybe you could be normal just with a small change, then you need to be protected. Only if you are guaranteed, quote unquote, to be abnormal in a data dependent sense, then we basically don't guarantee you privacy. Okay, so let's go ahead again. So privacy protection of every record that is or becomes normal under a small change in the database. And really, we came to this point. The intuition behind this was also looking at the definition, the outlier definitions as well. This notion of stability, that a small change in the database should not change the status of something, whether it is an anomaly or not. That is what is robust anomaly detection. And we want to actually follow that as well in the sensitive privacy framework. So again, a sensitive record is something that either is or becomes normal under a small change in the database. The way we quantify small change is the addition and or removal of K records, any K records, it doesn't matter, okay? And then this normal is what is called a normality property. You may define it in any particular way, whatever way you want. So the definition is totally general, okay? It doesn't restrict you in any way. And now the sensitive privacy definition is very, very similar to differential privacy. In fact, it's exactly the same, except for this underlined part. So we are going to guarantee privacy only in the case of databases that are differing by one record that is case sensitive. Okay, so we are now restricting the neighborhood function, if you will. Okay, that's what we are essentially doing. And just to show you what happens, because I said case sensitive, that's a new parameter. So what happens when K is 1, you have, of course, a set of things that are outliers. As you increase K, because remember it's addition or removal of K records, less and less things become outliers. So of course, if you have a very large K, then very little things will be anomalies. Okay, so that's the way it sort of grows. All right, now I'm going to sort of give you a very brief idea of the constructions. I won't spend a lot of time on this because I don't want to, I would rather just prefer to give you the impression of it. But just to give you an idea of why this works, okay, why DP versus SP works. Remember our example where I showed you these two neighbors and DP is guaranteed to do badly either here or here. The reason why sensitive privacy works very well is that these two neighbors, which have different answers, fx is 0 and fy is 1 for is this an anomaly, are not neighbors under sensitive privacy. So when we look from the sensitive privacy perspective, how far from X is the closest database that has a different answer. So you can basically see that, oh, you know what, I will need to add a record here first for a neighbor, then I can add a record here, then I can add a record there, blah, 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 move until all the way I come here. So the point is they were direct neighbors under DP, but they are not direct neighbors under SP. And then, depending on how long this chain is, that's it. That is the amount that we can relax things by. And in fact, we've characterized this through the notion of this minimum discrepant distance function. And what that does is basically just to say, okay, if you're looking at two things, basically for every possible pairs, we want to look at this distance. How long does it take in order to go from this to this? So I won't show you this, but let me just show you one thing, that basically if you have a metric over the types, you have a specific anomaly definition, and you know what are sensitive records, you can induce a metric over this graph. And this graph, by the way, is a graph of databases. Okay, it's not a graph of records. It's a graph of databases. In differential privacy, everything is connected to everything. Neighbors are connected, like this is connected, and so on. In sensitive privacy, some of these links are no longer there because they're not neighbors under the case sensitive records. Now, the constructions that we've developed two constructions. One is a compiler that takes any differentially private mechanism and makes it sensitively private. Okay, so if you have any differential private mechanism, and you have this delta, which is basically a lower bound for that relaxation. Okay, how much is the difference? Then we can just take that. We can take a sample from the mechanism and then set the probabilities appropriately and then return an answer. If you look at it, the mechanism itself is 3 lines. It's very, very easy. It's very efficient. You can go ahead and do this. Of course, there is a difficult part, this delta. How do you set this? But we've shown how you can do this in general to satisfy differential privacy. The other thing is with something like this, and this I'm totally not going to go into, but we can show that basically you take this mechanism U, and as long as M is valid, the base mechanism is epsilon by 2 differentially private, the delta is a lower bound on this difference, it slip shifts continuous, then this error is guaranteed. Okay, the probability that the error will occur is exponentially smaller than the error of the differentially private mechanism. So again, pictures work better than either symbols or words. So basically, if you have a really crappy differentially private mechanism, okay, that just does badly on everything, our mechanism will still improve it over here. If the mechanism is something non-trivial like this, it's still going to improve on all of this part, and you will, get better performance for the most part with something like this. So this, by the way, compiler is very general. It takes any differential private mechanism and then does this. Okay, so that's great. It works independent of whatever is the outlier notion or what have you. We did come up with a very specific SP mechanism as well for an arbitrary GI, where we directly lower bound. We don't look at the relaxation. We directly lower bound what would be the distance. So this lambda, if you will, we show you how to derive this. Now this, however, is specific to some extent. And then once you have that lambda, you again have a family of functions, the mechanism U lambda based on the lambda, which is similar to before, but again does a sampling and returns an answer, yes or no, based on what we come over here. Again, I won't go into this, but we've shown in the work that this is actually Pareto optimal. It's in fact great. And as long as lambda is smaller than this, in fact, even give you a differentially private answer. So it can work in that sense as well. And furthermore, the error is very, very low. Okay, so specifically for the distance-based outlier detection, the error is really small. In fact, it's less than -2 epsilon beta by 5. Remember, beta is typically very, very large, so the number of points you need to have close to you in order to be a non-anomaly. So it's very small. The error ends up being very small. For this, you have to find the lambda and then use the construction. And we've shown how to do that for the distance-based anomalies. You could extend it likewise as well. Just to give you a very short picture of what happens, we looked at it basically with a bunch of different data sets, real data sets, some synthetic data sets as well. And the only thing I want to point out is in each of these, the right side is basically differential privacy. It's stuck at 0.475, essentially because of the sparsity factor. The left is sensitive privacy, and the error that we get there is significantly lower. I mean, not significantly, it's exponentially lower. For a change, that word is actually correct, mathematically speaking. Okay, so it's exponentially lower than the error you get with differential privacy. So if you look from a F1 score perspective, we in fact looked at families of differential private mechanisms, in fact, also the optimal differentially private mechanism, and then our sensitive private mechanism. And generally across the board, it did orders of magnitude better over here. One last point that I want to make over here, which I'm not going to go into a lot of detail. Interestingly enough, for the normal records, the performance of DP and SP is exactly the same. Okay, it doesn't vary there. Where we do better is on the anomalous records and on the fully blank bar. Okay, that's where we do significantly better. And that's how, in general, we do better because most of things are empty space. So to be continued along these lines is to instantiate the construction for other anomaly definitions. Again, the definition of SP is very general, sensitive privacy, but in order to make the mechanism work, you have to instantiate the construction, so to speak. How can we find a good lambda? And there are a bunch of difficult or open problems. Outlier detection as a whole, okay, give me the actual outliers is very, very tough. That's much more difficult. Even having an optimal mechanism for querying the number of outliers is an interesting question to look at, or how we can do this with nearest neighbor-based models. So that's the overall picture on this. And if you are interested, please do look at our paper that has all of the math over there and goes into more detail on how this is actually achieved. Now I'm going to come back to what I promised you at the start, COVID hotspots, okay, and related back to that original question as well. Remember this picture that I showed you of existence independent versus existence dependent outlier queries. The good news for us is that detecting COVID hotspots is existence independent. It's basically where we are looking at, is there a pandemic or what are the hotspots? It does not depend on a single particular record, okay, any single record. So that means that we can actually go ahead and use, if you will, straight, differential privacy directly for this purpose. I apologize for that. So that's great. However, there are a bunch of challenges in this as well. And the real problem, if you will, is the fact that you need to worry about spatio-temporal privacy in this case. And it's not just that, you have to worry about the changing data. Remember, people are going to keep on putting in their symptomatic information every day. It's going to die away after a few days or what have you. The fact that data is changing. And even worse, the fact that you could have an arbitrary number of queries. Someone who's trying to attack could basically look at anything they wish and use this in any way they want is problematic. And then, of course, you have system level issues. You need things to be fast, usable results that are tuned to the situation. And believe it or not, it turned out to be a big, challenge to even have this done and have it in a way that was certified by, say, the Play Store and App Store. So there were issues from that perspective too. So this part, we were actually, by the way, focused on getting something actually working, both from a theoretical perspective, but then actually working so that people could use. So we have focused on that and come up with the system. It's not published. So I'm going to give you a little bit of idea of what is happening over here. And then you're, feel free to try things out as well. So the way things work is that similar to what you're doing right now, you would report your symptoms. And we have developed an app for actually doing that called the COVIDNearby app. It's available for both Android and iOS, and it's there in the Play Store and in the App Store. Also, there's a web app. So if you go to covidnearby.org, I'll show you how that looks. You can try and report the symptoms over there as well. That's sent to a database, which is stored securely. But now what we do is that every 24 hours, we basically look at the data of the past 14 days and turn it into an intermediate representation. So specifically, we are building quad trees, okay? And again, if you have worked in this area at all, you may ask, why not use something like KD trees, okay, something that would be better? And the answer is privacy, because it basically becomes a huge problem when you're using something that is data dependent. So we build a bunch of quad trees, and then when you ask a query, you can ask a very general query wherever you want, and then you get a differentially private guaranteed answer over that, and that is what will be provided to you. So in fact, very, very briefly, let me see if I can pull that up. That's, by the way, the app itself. So I have, if the first time you go there, you're going to see this sort of a survey. The next time it'll be very little, but basically, do you have symptoms? Have you been tested? Stuff like that. And you don't need to change this unless, of course, something has changed. So this part is very similar. Okay, nothing changes. And in the app, it's even easier because it's basically, you can just use it on your phone, so to speak. But now this is the interesting part, if you will, where you can go and you can look at specific parts. And right now, this is just the confirmed cases. So there's nothing special happening over here. This is coming from the same JSU sort of data. But if you toggle this thing over here, right, now you're getting answers from our particular system. So you know the number of people reporting symptoms and the number of people reporting no symptoms in any area, and it'll automatically change over here. You can zoom into specific places and get the specific answers. And this is real data, real life data that is coming from the system. The really cool part is that this is guaranteed to be differentially private, and it doesn't matter what people do, how many queries they ask, where they look at things from, it is guaranteed to be private no matter what. And I just wanted to show you, because we have the real data as well, not just the stuff that you're seeing over there, we actually get almost identical results with guaranteed privacy. So this bar chart that you see, there are 2 bars for every date. Actually, the bar on the left is the real count. The bar on the right is the so-called differentially private count. Okay, and you can basically see it's very, very similar. The heat maps make it nicer to look at basically on 3 separate days in a county. You get the same heat map. Over here, it's the same across the US. In fact, it's the same across all 5,000 counties in the US. And we did the Kale divergence test and a bunch of other things to look at this. And that works out fairly well in practice. So I do encourage you to try out the apps, the iOS app, the Google Play app, what have you, or look at this. And this is something my student came up with. It's pretty cool because it is differential private, so it is guaranteed to work. With that, I'll stop. That was it, and I have gone over. But please let me know if you have questions.
Thank you so much, Jaideep. That was a really, really impressive and exciting talk to hear. So thanks so much. There's a question on the chat from Corey Cornelius. Bill, could you unmute? Actually, I can probably unmute him. And
I can see this too.
Actually, let me. Corey, if you don't mind unmuting and asking your question, we'll get some interaction going as well. So please go ahead.
Yeah, can you actually hear me?
Yes.
Awesome. So I was just wondering about your definition of sensitive privacy. Is it,
right.
So if I understood correctly, you're sort of saying that people who are outliers,
right,
they would have no privacy, whereas people who are sort of in the normal, I guess, distribution would, not distribution, but population would have privacy, at least under the DP mechanism.
Correct. So to explain, yes, with a slight caveat. So the way we are defining things is that, first of all, this is still data dependent, so to speak. And what we are guaranteeing is that if you're normal, or you could potentially be normal as well. Okay. And this, by the way, the parameter K that you can set to decide, how much of a distance is needed for you to be normal, that is something that you can set, or the system designer can set. But if you could be potentially normal as well, you would still be protected. If you are indeed going to be an anomaly, even with that degree of change, then yes, you would. Basically, the thing is the anomaly identification or anomaly detection. The goal of that is to finally output those anomalies. So yes, in that case, your quote unquote name or record or whatever would be output, and you would essentially have no privacy. So that's true.
Yeah. So then in the case or the example you gave at the beginning with this Native
right.
American woman, it would basically de-anonymize her, right?
Right. So if we look at that particular case, actually the interesting part is in terms of aggregates, actually it depends on the specific question that you are asking. But with the sensitive privacy case, again, right. So from a health research perspective, if I was interested in knowing, are there people with these characteristics which are truly anomalous, then I would be able to retrieve those. Otherwise, it would end up being anonymous. That's true.
do you have examples of where this is actually useful? Like where, like, because that seems sort of ethically weird, but where is this actually useful?
Right. So in fact, so interestingly, this is what happens, okay? So what we've found, and that is actually the case, because by the way, when we started looking at this problem, we wanted to sort of do anomaly detection or anomaly identification while guaranteeing privacy. So, I'm a privacy researcher. So it makes perfect sense that we want to protect everyone. We always look at essentially the worst case scenario, right? While we were working on this, we essentially found out that for anomaly detection itself, forget about detection, in fact, for anomaly identification, as I said, it is impossible. There is no, we can guarantee that utility is going to essentially be horrible. That means that you can go along two different routes. Either you would not use this mechanism at all, okay, or you basically end up getting the data and nobody has privacy in any way, shape, or form, okay? And I've actually been working in the healthcare field, in the biomedical informatics field, let me put it this way. And it is very interesting because if you're trying to find sort of, do rare diseases, if you're working on something like that, it is really crucial to be able to get real data, but they are worried about the fact, what happens over there and to what extent can you trust the output of this. So I agree with you that from an ethical perspective, it may look that, oh, you're not protecting the people who really need to be protected, but I would rather reword it and say that this is more for the applications where we need to identify those people. Again, it could be for a reason that we can go ahead and help them in particular ways. That's not the only way it could be used, but that is one of the things. And it still does protect anyone who could potentially be normal. So in some sense, it would enable people to basically still participate, give them as much of a privacy guarantee as is possible. So yeah, I mean, I see the point, but there are application spaces where this is still useful.
Awesome. And so as a last follow-up, do you have experience with like institutional review boards and them understanding this?
That's a fantastic question. In fact, let me put it this way. Yes, we've had some discussions with the IRB, and we had to, in a different space. In fact, even for this, we were trying to, by the way, as part of the NSF RAPID project, we were also trying to understand privacy calculus. So that's the part that I'm not showing right now, but basically look at how people make decisions, in extreme situations over here. And having that conversation is difficult, but in fact, we are going through with another research study where we are actually getting people from the IRB to be on board to see if we can sort of try to do things in a sort of two-step form. So if you worked in the medical field at all, data and data use agreements are serious, like, time sink, if you will. So are there ways in which we can figure out if there is value to the data, perhaps by using approaches like this to do exploratory analysis, coupling it with sort of some synthetic data generation, and IRB could expedite things like that, really expedite, not just the expedited form, if you will. And if that works and you need access to the real data, then you can go through the entire data use sort of agreement. But we are trying to work on that. I mean, that is always an ongoing process. So.
Thanks.
Jaideep, and thank you for that fascinating set of questions, Corey. Can I ask other members of the audience if they'd like to ask any more questions? So, Jaideep, I have a question.
Sure.
It goes back to the original example of the Native American woman,
right.
75-year-old being identified. You said you solved that problem by encoding the problem of inferring those missing attributes as some kind of either linear programming or integer programming problem.
Right.
Would you be willing to say a little more about that?
Sure, absolutely. And in fact,
what the objective function, what the constraints might look like in that case?
Sure. And let me actually go back over here, since I do not have this, but I can definitely.
Yeah, I'm not looking for the full details. Just
no. It's quite easy, but that's true. So the point is, here. something of this sort, right? So what we are looking at is this specific thing over here, where we have these variables. So the constraints are going to be for each row. For example, you would have a constraint that basically says, x11 plus x12 plus x13, 14, 15, and 16 equal 3 minus 1, that is 2. So every row gives you one linear constraint in the variables. Every column, it's the same thing. I can have, for example, x11 plus x51 equal to 82 minus these three things, okay? And then after that, I can just run something that says, so I have a bunch of constraints, and now I say maximize, the objective is to maximize x11 subject to all of these. Similarly, minimize x11 subject to all of these, and also the additional constraints that all of these have to be less than 10. They have to be integral, so you're right, it's an integer programming problem. And the fact that they're coming from less than 2 institutions. But yes, so I can run the max and the min problem for each one of these things, and then very easily. So you can use any solver to use C++, basically. Right.
I see. Yeah, very interesting.
Right.
Would it be possible put this in reverse? So what I mean by that is, you've got these constraints, and maybe what I do is to take a possible table, okay?
Right.
So I take this table with none of the values filled in. I have a variable for every value, every possible value. So I have a variable for every entry in this table. And then what I do is the opposite of what I did in order to disclose. I look at what you got and I say, well, I'm going to write down some constraints which ensures that any solution of the resulting system of constraints has at least so much error in in it, okay? And in some sense, that error is the margin of, the size of the
uncertainty, exactly, right.
That I'm willing to live with. So I might say, well, you can't identify this person as being one of less than, say, 30 people, okay? 300. So I should be able to write down some constraints and then solve that system of constraints to tell me what to put
in
each of those entries.
Right. No, absolutely. And that's a great idea, and that's absolutely feasible, because then the objective can be to, of course, perturb these things as little as possible in the aggregate. It would be interesting. The one challenge over there is that, yes, you can do this for example, this table. We need to do this basically for all possible questions. So you need to sort of formulate this and run that huge number of problems and somewhat efficiently. And then, that would actually be a system that could sit in between. And the good news there is that it would not be changing things too much. So it would be just working off of this, as opposed to, say, using something like differential privacy, where you have no control over how much noise is injected into any given cell.
Right. Okay, that was just a thought that occurred to me.
Right. No, absolutely. No, that's true. In fact, I should point out that with Eduardo, I had worked on a little bit, not this thing directly, but we were basically looking, I think he had worked on this inverse, frequent set mining sort of problems as well. And we were basically trying to say, can you create synthetic data that is not too different and still gives you this sort of region of uncertainty, if you will. So, right.
So we've got a paper in HCUP last year, and another journal paper we're just wrapping up, that looks at how to generate synthetic data.
Right.
Satisfies column-wise distributions, well as certain integrity constraints. Every kind of integrity constraint, but certain kinds. It's a very different approach. It's more a generative model.
Right.
Using a GAN-like method.
GAN-like, I see. Right.
Yeah.
Right.
But I think what you've done looks amazing. So anyway. So let me throw open the floor for any other questions. I see we're losing people as we wait, but are there any other questions from the audience? Well, if not, Jaideep, let me thank you again for a very thought-provoking talk. As we all know, the ability to identify anomalies is critical for lots of things, many of which you've mentioned today. I'm also very excited about your COVIDNearby app and website. And, I don't want to ask this question now so people can sort of get out of here. But of course, there are interesting questions on what you plan to do with the data that you collect there, which might have, really interesting applications. So
Right.
thank you so much for taking the time and trouble to talk to us during this,
That was my pleasure. So
this
thank you.
online forum. And again, really appreciate you doing it. Okay, so thank you. Excellent talk. So, I'm going to clap.
Thank you.
Not everybody else might be able to do that, in a verbally valid, in a audio valid way, but thanks so much.